we learn from the phase diagram into the application. Okay, for this one, the application we call it thermal processing. Okay, of a metal, especially in this module, we specify in iron or steel. Okay, iron carbon. So at the end of this lesson, you should be able to understand the procedures of annealing and normalizing. What is annealing? I think we have discussed this in the chapter 4. And normalizing is the same process, which is a heat treatment process, but different, slightly different procedure. Number 2, you should be able to understand quenching and tempering process, another heat treatment process or thermal processing. And then understand how heat treatment affects the mechanical behavior of metal. Okay, in particular, steel. Okay, when a metal is plastically deformed by cold working, right? We have discussed this in chapter 4. The metal becomes strain hardened. Strain hardened. Okay, why? It is because an increase in strength and a decrease in the ductility. Okay, it's because there are several mechanisms that increase its strength and reduce its ductility through the increase in the number of dislocation or the entanglement of the dislocation. So the material become hardened. Okay, so this is a typical schematic diagram, displays the microstructure changes after the plastic deformation, or we call the process as cold working process. Okay, cold working process. Okay, there are several processes, but one of them is rolling. This is rolling. Okay, rolling process. So in module 4, we talk about a strengthening mechanism through this process. How the metal becomes high strength because of this process. Okay, this strength harden actually can be removed by annealing process. Yes, we have discussed in the module 4. Okay, during the rapid solidification of many alloys, okay, rapid solidification. Okay, what happened is compositional gradients are created and core structure are produced. Core structure are produced, meaning that surface and at the structure as the surface and the surface is not similar. Okay, that's it become core structure. Okay, surface and in center is not similar. Okay, like this. This is near the surface. This is at the middle, the center region. Okay. So compositional gradient throughout the grain, right? So meaning that the properties is not similar. When you give a load at, for example, at this direction, their response to the load at this point differently because they have different properties. Okay, core structure effect can be removed by a heat treatment process. Okay, we call it a heat treatment process. So through the heat treatment process, it can be annealing, it can be normalizing, where during this process, the core structure can be eliminated by homogenizing the cast alloy. Okay, we make it homogenized for a very long time at a high temperature. Okay, just below the melting temperature of the lowest melting phases in the alloy. Okay, for example, there are two phases, phase alpha / beta in the lamellar structure, for example. So either this alpha phase or beta phase, you need to obtain information which phase having lowest melting point. Then you should choose that as a reference, where you need to ensure that your heat treatment process conducted at temperature below the lowest melting temperature of the phases present in your alloy. Okay. Uh, Heat treatment is a process of heating and cooling of metals using specific methods to obtain desired mechanical properties. Okay, we have annealing, we have normalizing, quenching, tempering. Okay, there are some of heat treatment process for metal such as steel. Okay, it is very important. Casting the materials, and then um, you can customize it. Okay, whatever the mechanical properties that you want. Okay, we are always referring to the phase diagram. For example, in this case, we talk about iron carbon phase diagram because our metal are steel. Okay, so all right. The annealing. Okay, sorry. Okay, for process, okay, we have several processes. We are always referring to phase diagram. For example, if you want to conduct process annealing, you are this process annealing suitable for this grade of alloy. Okay, higher than that we don't call a process annealing, and the temperature range between this. So that one is process annealing. If we have high carbon content, which is almost, you take the composition, maybe starting from 0.61% carbon and up until the maximum steel composition. Okay, this one, if you want to conduct a heat treatment process, you need to select a temperature just below the ear temperature. What temperature? It is 7 to 7 degrees Celsius. Okay, this is eutectoid temperature. And then the temperature is about plus minus 50 degree. No, plus minus, meaning that's 50 degree below the AC1 line. All right. This method, we call it ferrodizing anneal. Okay. Why we give a different name? Because during you conduct the process, the mechanism differently. Okay. The mechanism where they change the properties occur differently. So we differentiate it by name. Okay. And then there are another process called normalizing. Okay, normalizing, and other are full annealing and hardening. Okay, normalizing, basically you can have for any composition of the steel, and the temperature is about 50 to 100 degree above. It is about 50 degrees Celsius above the AC3 lines. Okay, and for full annealing, different types of composition, different range of temperature. For example, if your composition is about 0 until 0.8, so you select a temperature in this region. But if your alloy is hyper eutectic alloy, you can select this range of temperature for full annealing process. Okay. So annealing. Okay, what is annealing? Annealing is actually a process where we introduce heat, and then we allow the changes on the microstructure. Okay, and when the microstructure is changed, the microstructure, okay, and what happens is the mechanical or electrical properties will also change. Okay, typically for metals such as steel, annealing is used to reduce hardness, okay, increase ductility, and help to eliminate internal stress. Okay, internal stress. Three most common annealing process are, we have full annealing, full process, full annealing, process annealing, and spheroidizing annealing. Okay, but the two most common types of annealing, we usually use full annealing and process annealing. These two are most commonly used. For spheroidizing, it's a method for, if you look at this spheroidizing process, it is for high carbon steel. Okay, when we use high carbon steel, why high carbon steel? Because the carbon content is very high. Okay, it is high carbon content. So basically, we want it to be strong and hard. So that's the reason when you have this kind of alloy, we uh, we uh, we are not really frequent heat treated it, okay? Because the spheroidizing process will reduce the strength and will promote the ductility. So that's the reason this is very seldom being applied in the industry, because we really want the high carbon steel to be high strength. So the full annealing. Full annealing is often utilized in steel that will be machined or will experience extensive plastic deformation during forming process. Okay, so this is full annealing. This heat treatment is performed to produce coarser microstructure, okay, which will increase its ductility. Okay, coarser microstructure. Okay, why? Because for example, if there's a very complex structure, okay, product of component, okay, you need to conduct several machining process. For example, to produce what? Let me guess. Okay, for example, a gear like this. Okay, for example, this is a gear. Okay, after casting, or maybe it depends. If it is casting, it's okay. But if it's coming from, let's say this is a complex, not gear, okay? This is a complex shape of structure. Before it become like this, it is looks like this, all right? And then you cut it extensively at this region, all right? See, there are several machining processes. After cut, you need to trim the surface, but also by machining. Okay, you trim the surface. So there are multiple machining process. You trim the surface, okay, and it takes a very long process because you need to achieve, for example, the design requirement require you to make it a very smooth surface, okay, because it's experience abrasion, okay, during the operating. So you need to design it as smooth as possible. So for that case, between the machine process, they conduct full annealing process. Okay, they don't want this to be hard, so they are freely to treat this structure to obtain the ductile properties. Okay, so through this heat treatment process, you will get coarse microstructure. Okay, so coarse microstructure, remember, okay, if you have two different microstructure, for example, this coarse, this is fine microstructure. Okay, so which one is a stronger, or which one is more ductile, or A or B?
E.
A. Okay, so the full annealing process ultimately you will obtain the coarse microstructure. So if your material becomes soft or ductile, then you can proceed with the next machining process. Machining process, whatever this is only one example. Machining process. Maybe you can conduct if the process involve co-working process, for example, rolling, stamping, or whatsoever. So the co-working process can be conducted on a coarse or ductile materials rather than hard materials after several co-working process at the beginning. Okay. So example full annealing of hypoelectric steel. Okay, this is AC3, the temperature. you conduct, it is about 50 degree above the AC3. Okay, where is AC3? You go back to the slide, earlier slide, okay, which is this one. Okay, this is AC3. Right. For example, we want to conduct the full annealing process for the hypo. Okay, where is hypo? Eutextile, this is hypo. Okay, this is hyper. So now you know the types of steel. One is hypo, one is hyper. For hypo, this is the AC3 line. Okay, this is AC3 line. For hyper, this is AC3 line, ACM line. Okay, AC3 belongs to the hypo. So you need to select extra 50 degree above this line. So meaning that around this point, this is the point. Okay, what is the composition of your alloy? You need to identify. Let's say it is 0.4. So okay. Okay, let's say your alloy is 0.4. Okay, this is the AC3 point. So it is a 770 degrees Celsius. You need to put an extra 50 degrees Celsius. This is how you determine the temperature. Okay, you cannot simply choose the temperature that you want. Okay, there's a rules that you have to follow, which is if it is hypoeutectoid alloy, you need to take this region. Okay, if hypereutectoid alloy, you take from this region. Okay, so this is the temperature that you choose. Okay, so heating process, you increase the temperature at this level, and then step number 2 is soaking. Okay, it depends on the size of your sample. Okay, if it is too short of soaking time, maybe not all microstructure uh, um, will change into coarse structure, coarse grade. So right, for the hypoeutectoid steel, okay, you increase at this temperature. What happened is it's become into a different microstructure. Okay, and it is austenite. Okay, so soaking time will take some time to allow sufficient transfer complete transformation into austenite microstructure. Okay, so that's the reason you need to choose above AC3, because we want to obtain austenite microstructure. So if you look at this phase diagram, okay, where is the austenite microstructure? Okay, remember for the last class we talked about phases present in the phase diagram, right? Here is austenite. Sorry. Okay, this is austenite, which is gamma. Okay, so if your alloy is hypoeutectoid alloy, let's say 0.4% carbon, okay, you heat at this temperature, which is 50 degree above the AC3 lines. Okay, then you need to soak until this alpha plus cementite microstructure completely transform into austenite. So that's the reasons the step involve a soaking process. Okay, so these are the steps. Okay, so number 2, we do the soaking process, okay, to allow the phase transformation from the alpha plus perlite ataupun alpha plus cementite into a microstructure of austenite. Okay, and after it's completely transformed, how to determine basically you need to experimentally investigate the transformation, whether it is completely transformed or not. So basically, if you are working in the industry that's involved this kind of process, they have the standards for that. Okay, small sample, how long it will take, large sample, how long it will take. Okay, basically they have the standard. Okay, because it is supposed to based on the experimental work. Okay, and then this is the most important thing, the cooling process. Okay, it is a furnace cool. It took 30 hours of cooling process. What is furnace cool? Furnace cool means you turn off the furnace and let it cool slowly, following the temperature reduction of the furnace. Or maybe you can control the you can control the uh, temperature reduction in the furnace. Okay, for example, you reduce the temperature. Temperatures, for example, it start from 820 degrees Celsius. All right. Okay, you reduce uh, 20 degrees Celsius per hour, for example. Okay, or maybe you decrease 2 degrees Celsius per hour. So how long will it take until you reach 24 degrees Celsius of room temperature or 25 degrees Celsius of room temperature. So it is a furnace cool, meaning that it's controlled by furnace. Okay. And then what you get is a new microstructure. Of course, you still have the same type of phases, which is this is a pro-eutectoid ferrite ataupun alpha, and this one is a perlite. Similar to this one, perlite and alpha. However, the grain size is different. Okay, grain size is different. Okay, it is a coarse microstructure. Okay, and for the composition in excess of eutectoid, it is 50 degrees Celsius above the ACM line. No, above the AC1 line. Okay, for full annealing. Okay, austenitizing. Okay, austenitizing. What is austenitizing? Okay, when we heat the steel, okay, above the SCM for hypoeutectoid and AC3 for hypoeutectoid and ACM for hypereutectoid. So we will get austenite. So we call it austenitizing process. Okay. The BCC will transform into FCC structure. Okay. So this is in the room temperature BCC structure. And then we heat it up until we reach into austenite. Okay. Cemented from perlite disintegrating upon heating. And then later it will produce pro-eutectoid phase. Okay, ferrite will transform into austenite slowly. Okay, and then you will obtain austenite. Okay, this is during the heating process. Okay, this is during the heating. It is not difficult to remember this or to understand it. Okay, if you still remember during the last class, okay, during the cooling process, it's happened reversely. Okay, from austenite to the formation of pro-eutectoid phases at the grain boundary, and then after it reached a temperature 727 degrees Celsius of the eutectoid temperature. All right, you will obtain perlite, and then it's continue until all austenite transform into perlite. But reversely, if you do heating process during the full annealing process, it is happen okay in the reverse mode. The next process is process annealing. Okay, process annealing is a process that we conduct at a slightly, not slightly, at lower temperature. And the purpose is just to uh, relieve the stress. Okay. We don't change the microstructure. Okay. It's a heat treatment that is used to remove the effect of cold work. Okay. For steel, this treatment is usually applied to hypoeutected steel with less than 0.3% carbon. Okay, because the what we call it okay, during the co-working process, okay, despite the distort microstructure and the residual stress in the materials, okay, uh, sorry, okay, the co-working effects will increase the strength by the grain distortion as well as the um, increment in the residual stress. Okay. However, for a certain application, the strength contributed by residual stress is not needed. Okay. So it may cause other failure. So to remove this residual stress, okay, we can do that by process annealing. Okay. But the strength that we obtain from the co-working process uh, slightly reduced, but still you need to measure so that we have an appropriate increase in the strength after the co-working process. Okay, when we conduct the process annealing, uh, it slightly reduce the strength, but still meet the design requirement. Okay, basically we conduct this for the 0.3% carbon. Okay, usually the temperature you have seen it in the diagram earlier. So okay. Sorry. Okay. Uh, okay, sorry. For the effect of co-working process is combines from not only release the stress but also um, modify the microstructure that's obtained by the co-working process. Okay, the distortion of microstructure also um, can be modified during the co-working process, but for this process, the temperature is about 550 until 650, and it's only dedicated for the very low carbon composition. Okay. For example, okay, at this temperature, which is lower than AC1 temperature, okay, uh, highly deformed microstructure after co-working process, okay, we prolong the soaking time until we can generate the uh, nucleation, new grain formation. Okay, and then but for this case, there is no arsenide formation. Okay, because the temperature is lower than AC 1 degree Celsius. But to obtain this grain recovery, okay, where if you cool it slowly, you can get a similar for the full annealing. But this process annealing, where the temperature is lower than um, eutectic temperature, uh, is not involve the formation of arsenide, and the limits is only up until 0.3% carbon. Okay. So there's no phase transformation. Okay, microstructure will retain. Okay, this treatment is performed to convert lamella cementite into spheroidite structure. Okay, why lamella becomes spheroidite? Because spheroidite is a structure where um, uh, higher ductility will obtain. Okay, so we call this process spheroidizing. Why spheroidizing? Because the lamella inside the pearlite will become a spheroid. Okay, for example, like this. Okay, this is cementite. Okay, the blue line. It is cementite. And then at this temperature, which is a temperature lower than 7 to 7 degrees Celsius, okay, the transformation of this cementite inside the pearlite will become spheroid. Okay, spheroids still have a maximum softness and ductility and are easily machined or deformed. Okay, so this heat treatment is generally applied to hyper-eutectic steel. Okay, the temperature just below the AC1 line, which is this line is 7 to 7 degrees Celsius. Okay, and then cementite impolite, which is in the lamella structure, will transform into spheroidal cementite between 15 to 25 hours. Okay, this is what happened. After transform completely, we do a slow, very slow cooling, which is in the furnace cooling. All right. Uh, that's it for the annealing. Annealing involves full annealing, process annealing, and spheroidizing. Next is normalizing. Okay. The difference between annealing and normalizing is the method during cooling process. Okay. In normalizing process, we use air cool. So meaning that we conduct the cooling process in the air. Okay. So the purpose for normalizing is varied. Some of these are to refine the grain structure, okay, to increase the strength. Of course, if we obtain a smaller grain structure, we can increase the strength, okay. So basically, the steel that cool at in the air, okay, means experience normalizing process will have higher strength compared to the annealed steel, okay, for the same composition. To reduce the compositional segregation in the casting or forging and thus provide more uniform structure. Okay, for example, as we discussed earlier, where there are core structure, where in the casting process, okay, structure at the surface is different compared to the core. So we also can conduct normalizing process to make it a uniform microstructure. Okay, example of hyper-eutectic steel. Okay, again you refer to the phase diagram. What is the temperature for the normalizing of hyper-eutectic steel? We hit above the A3 line. Okay, AC3 line. Right, this is our microstructure, and after soaking, it will become arsenite. Okay, and then slow cool. The air cool, we got slightly smaller and homogeneous. This one is not homogeneous. Okay, some region are small, some region are large, but after the normalizing process, you can get an equate shape of the grain, either pearlite or ferrite. Okay, this is a ferrite, and this is pearlite. Okay, so we make it homogeneous and the size slightly small. Okay, for the hyper-eutectoid, still are done by hyper-eutectoid. The temperature is 55 degrees Celsius above ACM. Okay, ACM line. Okay, you can refer to the phase diagram. Right, quenching and tempering. quenching is a fast cooling. Okay, fast cooling. All right. Okay, to obtain to conduct quenching process, okay, after quenching, it will form a new phase. New phase to obtain. Okay, previously when we talk about, okay, sorry, this one is not relevant. Okay, uh, for quenching process, you will obtain new phase. Okay, new phase. So one regulation to get new phase other than the original phase, which is alpha and cementine. Okay, to get a new phase, you need to eliminate this first, meaning that you need to change it into austenite. So after you obtain austenite, then during the cooling, you can get new phase. Okay, if you want to remain as the original one, which is still alpha and cementine, you can cool it slowly. But if you want it to be new phase, you need to increase the rate of cooling process. Okay. So austenizing, remember whatever the composition, you need to always refer to what is temperature that you can obtain austenite phase. This is austenite phase. If this is your composition, you need to obtain temperature at this region. Okay. So okay, fast cooling, it can be we call it quenching process. It can be air. Okay, why air? Just now we talk about normalizing. It is a cooling in the air. But actually, you can obtain the effect of quenching. Let's say this compare between these two sides. Okay, this is large, this is small. All right, for small component like this, if you cool it in the air, it will experience quenching because for it is very fast cooling. But if your component is large, you cool it in the air, maybe you just obtain an effect of normalizing process. But when we talk about rapid cooling, quenching, for a component, large component like this, we require medium for quenching process, such as water, oil. These are the example of the media. All right. So after conducting quenching process, we conduct a hardening process. The process name is tempering process. Okay. The purpose is to harden the materials. Okay. Uh, we call it tempering. Oh. Okay. If hardening and tempering can be differentiated in terms of the tempering process. Okay. Uh, if you conduct the next step of the treatment process at lower temperature, okay, you can call it hardening because after quenching process, okay, the material become very hard, right? You do this treatment, okay, you softening it, okay, you lowering down the hardness, okay, and you can maintain the properties of hardness. But if you do the post-heat treatment process after quenching at high temperature, you can further reduce the hardness, but increase the ductility where the combination will promote the strength of the materials. Okay, so high strength is not always um, hard. Okay, strength and hard at one point it will become very contrast. Okay, all right. Quenching is a process of rapid cooling of materials after the heat treatment using a media, which is water, oil, or air. Okay, in this process, phase transformation um, at lower temperature do not occur. Okay, so in general, for metal, quenching can reduce the crystal grain size of material, and it is purposely to increase the hardness. Okay, especially for steel, this process is mainly applied to harden the steel. Okay, What happened during the when the steel is quenching? Okay, it form new phase. Okay, we call it martensite. Okay, after austernizing, okay, upon a rapid cooling during the transition between BCC to FCC, or the yes, you obtain um, BCC structure. Carbon atom, okay, sepatutnya supposed to in the normal condition, if you cool it down, you will get from arsenide FCC, you will obtain BCC. Okay, because this carbon is diffused out and it will form combine with numbers of atoms to form cementite. Okay, this is normal. If you pull it slowly in the air or in the furnace, you will get FCC transform into BCC. Okay. Um, However, if you do the cooling at very uh, very high rate, okay, fast cooling, okay, this carbon atom cannot diffuse out, okay, out from the FCC unit cell. Okay, it will now trap inside the BCC ferrite. Okay, so it trapped into the BCC ferrite. So the BCC elementary cell of the ferrite structure are expanded tetragonally. Okay, by the carbon atoms. This tetragonal structure call it BCT, body centered tetragonal. Okay, this is BCC, this is FCC. Okay, so body centered tetragonal structure is a new phase. Okay, this one is a we call it austenite, right? Austenite. This one is ferrite. Okay, ferrite. So this one is new one, BCT, which is we call it martensite. So in the first diagram, there's no martensite. Okay, no martensite. This happened because the reaction is non-equilibrium. Okay, remember last time one student asked me what is a equilibrium phase diagram. I just explained very roughly. It is a stable transformation. Okay, upon cooling from austenite to BCC structure, it is happened slowly. The mechanism of diffusion occur homogeneously and in the equilibrium mechanism. Okay, but for the fast rapid cooling like this reaction we call it non-equilibrium, a very fast reaction. So that's the reason you get martensite. This one is not formed during constructing phase diagram. Okay, if you want to construct phase diagram, remember the process to make a phase diagram. It is based on the heat treatment process. It's based on the experimental work where people conduct it at a very slow cooling process. Okay, to obtain a equilibrium structure. Okay, this one is non-equilibrium. Okay, so if we observe under microstructure, if we observe under microscope, this is the microstructure of martensite. Okay, example for hyper-eutated. Why hyper-eutated? Because the composition is larger than 0.77% carbon. Okay, so after quench, what you can see is a needle-like structure. Okay, something like this, needle-like structure. Okay, this called martensite. Okay, martensite itu bentuknya macam tajam macam tu. Right, pure martensite has no slip plate. Okay, also only certain FCC will transform into BCT structure, body centered tetragonal, due to number of carbon atoms. Okay, and this will cause lattice distortion. All right. So because of this, if you have a certain amount of carbon, it depends on the numbers of carbon atoms. Some of the steel where the amount of carbon is too low, you don't obtain the martensite structure. Okay, because it is contain less insufficient amount of carbon to form a BCT structure. Okay, to be trapped in the FCC structure. Right. Okay, because of the lattice distortion, okay, dislocation throughout steel will have its motion obstructed. Okay, means that obstacle is everywhere due to the needle shape. Okay, there's no slip system at all. So that's the reason your material become very hard. Okay, so however, hardness is always associated with the brittle. Okay, therefore this steel is too brittle for any application. We don't use martensite for any application. Okay, so if you use it, you can easily find cracks everywhere. Okay, this is the crack. Okay, nucleation of crack in the steel with martensite fracture. Okay, because of the needle-like structure, there's so many stress concentration. Needle-like structure, stress concentration, very fragile, weak structure. Okay, if you have nodular structure like a spheroidization, remember spheroidite process, okay, turn the lamellar structure of a cementite in the lamellar structure into spheroidite like this, you will obtain very soft steel. Okay, this one is contribute to the softness of the material. But a needle like structure like this, there are so many stress concentration. It's easily cause material brittles. Okay, senang nak crack. All right. The tempering process. Tempering is a treatment of reheating. Okay, after we conduct quenching, we conduct the tempering process. It's the next process right after quenching. Okay, after we obtained martensite. Okay, we only obtain martensite through quenching. Okay, this process, the job of this process to treat this martensite, to reduce the brittleness. Right? So the heating will be done below eutectic temperature, okay, which is 7 to 7 degrees Celsius, to prevent astronite transformation. Nanti tak nak balik, nanti kan patah balik tak siap-siap lah kan. Okay, this process will soften the martensite, okay, by transforming it into a structure of iron carbide particles in a matrix of ferrite. Okay, so I think we should stop now because it is 3:50. We will continue this lesson in next 2 weeks. Okay, after the mid-semester break. So I think that's all for today. Do you have any question?
No, Doctor.
Okay. So do you understand or which one yang you rasa very difficult? Oh, biasa-biasa je, senang je. Can you follow? Because this is very important, I think. This heat treatment process, it's widely applied in the industry. Whatever the process you conduct, there are always heat treatment process. Okay, this is part of the topic lah. All right, if you don't have any question, I think we stop here. The attendance, have you scanned the attendance?
No, Doctor. No, Doctor.
No. Okay, I will share the screen. Semua balik raya ke?